about how we're actually, sorry, I'm going to be talking to you about how we're actually using genomic selection within all stages of our program. And then I'll touch on a little bit in economics, but not too terribly much. So winter crops especially, our timeline between when we take those plants out of the ground and have to make our selections to plant them again is very tight. We have between July and September to make those decisions, and we're looking at the agronomics of them, the disease traits, and malt quality. However, we can't actually get malt quality, like not all of our phenotypes can be collected before we make those decisions. So we have the short time frame to make those. And ways we're using genomic selection within our program are with same season selection. So for those traits that we can't actually get the trait or the data in the field before we make the selection, how we're increasing the selection intensity, and mate pair selection. So first off, same season selection. We collect our quality samples for malt in the summer. We send them off. We get the data back in the winter, sometimes early spring. Not a very helpful time when we need that information to plant them again in the fall. But as it was just discussed, we can predict them. And our malting quality traits have a pretty good predictive ability within our program. However, that does require our year one materials to be genotyped before we harvest them in the summer. This figure was done, and this work right here in particular with our predictive ability was done by a former student in our lab whose paper is in press now, which is exciting. I'm going to specify a little bit on GN and how we're predicting that right now. GN, glycosidic nitrile, it's the precursor for, as a carbamate, the carcinogen when whiskey gets distilled. And we're looking to start selecting for GN zeros, which have less than 0.5 parts per million. How we started doing that is in 2023, we took 220 of our known elite line, or our elite lines, and 2 GN0 checks from Pat Hayes' program that are now both released, actually, GN0 Vivar and Top Shelf, as Margaret was just talking about. We got those assayed, and it came back that, as what we expected, our program has no GN0s. So from there, we got the actual 95 of them quantified for their values, and this was the distribution in 2023, most in that low GN range. And the heritability was not great. So we don't have any GNs in our program, save the 2 that we have from Pat Hayes. A parent of those lines, Calypso, is actually a high producer. So that gives us some hope that we can, even if they have high lines, we can get low GN zeros. But with the heritability being 0.2, can we even select for GN? So we repeated some information between 2023 and 2024, and the predictive ability was moderate, about 0.5, with just using 2023, 2024, like across all. But if that was the G by E effect of that, if it's not repeatable across years, you can't really predict it. And between 23 and 24, it was repeatable with a fairly high correlation, genotypically and phenotypically. And so from there, we did a bidirectional genomic selection on it. We took the 16 lowest predicted lines and the 16 highest predicted lines, randomized them together, got them quantified, and the lows were lows and the highs were highs. And it was statistically significant. So we are able to predict for them. And at this point, we actually do have some families in our program that have entered year 1 trials this year, which is exciting to say the least. But moving on, how can we increase selection intensity within the program? Breeder equation, we've all seen this at some point or another. We want to focus on increasing the intensity of the selection. But so how can we do that when the amount of land we have isn't going to change? The number of plots that we can do can change from year to year, but not necessarily. So how are we able to get more lines without more space or other resources? And we're using sparse testing to do that. Each family gets split across 2 locations in our year 1 trials. And so every family gets, oops, too early. Each family gets represented in both locations, but each individual is only in one. So we're able to use genomic selection to fill in the gaps for the individuals that aren't in the opposite location by using their family members to predict that information. We began using sparse testing in the Barley program at Virginia Tech in 2023. And so, but prior to that, the number of entries was about half of the total plots we had, whereas starting in 2023, the number of entries is essentially doubled, closer to our number of plots. Now, the total number of plots does not include replicated checks, which help validate. But across the time, like, our number of plots is roughly the same. The number of plots within each of our testing locations that we use is also about the same. Now, I don't have any real data to show it's actually working in the barley yet, so I'm going to switch gears for a hot second and talk about how we're doing it in our wheat program. It's a little bit more complex. We have a trial exchange network with Jessica Rukowski in Illinois, Noah DeWitt in Louisiana, and Rick Boyles in South Carolina. If anyone is interested in doing this for barley, let me know. But our PhD in our program, Sun Frias, is doing a lot of work with this. So not all individuals are in every location. There is a slight overlap of, that is not showing up there very well. I'm so sorry. I just realized lines don't look great on there. That's okay. But so not every individual is repeated in every location. But every family, again, is still repeated. And we're able to add locations without increasing resources. And because of sending our year 1 wheat lines to other locations, we're getting an early insight on the G/E effects of them instead of having to wait for those later trials. In 2022, we only had 3 locations. We started with expanding in South Carolina, and predictive ability within year is high. And we're now up to 5 locations. So none of this would be possible without timely genotyping that we get with the USDA small grains genotyping labs. Right now, we have about 26 individuals that we're doing across 24,000 markers. And then our phenotype database is growing each year. And so we're getting close to the amount of data that we need for genomic selection to be even more reliable. We're also using it for mate pair selection, and that's actually a bit more complicated and challenging than I wish it could be. You have, say, you end up with 100 parents, and you can make about 5,000 crosses. So how do you decide which ones to make? And when you're trying to decide which ones to make, how are you optimizing the conflicting number of traits that you're trying to improve between agronomics and quality and disease? But then also each day in the greenhouse, I can make my wish list of crosses, and I have each year I have wish list of crosses I want to make. But the likelihood of me getting to actually make those is almost, some days is not possible at all, because it just depends on what's ready that day between what's been emasculated and what pollen is ready to be used. And so create a selection index, which when you're trying to incorporate a multitude of traits, it's kind of just you assign them based on what feels right at the moment. And this is an example of what I look at when I am making a cross in the greenhouse. I have it ordered by my feels like index, and you can see it's mostly weighted on grain yield, but that top cross, if I were to make it, is going to be lower in beta glucan. No, yeah, very low in beta glucan, and it's also the average of the means. It's not like, okay, I'm going to make this cross and you're going to get an individual with all of this. This is just the average of the expected mean of the family. So an actual economic analysis is not something that we've done. So this is just an overview of the economics of genomic selection. We're subsidized by the USDA genotyping labs through the Small Grains Genomics Initiative, but we are able to increase the number of lines significantly without changing the resources we're putting into it. That's allowing more opportunities for surprises because you get more lines out in the field that probably would have been dropped at some way earlier than we see them. But also the efficacy of mate pair selection with it is still currently unknown. However, this process has allowed us to release Fuller, which is a 2-row winter malting barley this year, using all of these processes, and it's doing well. It's high yielding, it has fairly good resistance to most traits, and it has good malt quality. So with that, I would like to thank the U.S. Wheat and Barley Scab Initiative, Spirits Board, Harmony for all of her work and help that she's done with me, the Malt Quality Lab, and AMDA for funding in the Small Grains Board and Spirits Board. I will take any questions.
Do you have any questions? Okay, well, thank you very much for your time. You did a good job.
All right, we're going to keep it in the state of Virginia. Our next speaker is Dr. Nicholas San Antonio, who will take a bit of a, it sounds like, shift in tone. We're going to talk about coordinated nurseries. Let's see where you go.